In this video, we'll move into section 1.5, where we will formally introduce the concept of a limit. Now, as you can note on the top of my page, I am introducing a limit, but we're not actually getting a very heavy math definition for a limit. We're actually going to start with what the book calls an intuitive definition. Let's get the idea and the understanding of it. And then when we look at the very math-heavy definition, it looks very ugly, but once we already have the basics established, then we could actually start to make sense of how that definition supports everything that we have been doing. So, the book also suggests that looking at that tangent line in the previous section and realizing that secant lines can lead to tangent lines is kind of their introduction to a limit, but I want to start just a slightly different one. Let's just say you're looking and you're starting right here and you want to finish moving to here. But as you move, we are just going to move in a simple straight line. But as we move, our little rule is that when we move, we can only move half the distance at a time. So in my first move, I make a big move. I'm trying to get to here, and I just take off half right off the bat. So I just made a huge jump, and now I'm here. But now as I keep going, well, now I do another half, and from here to here, that halfway point would take me about to here. And now I'm not going quite as far. And again, now I do another half, but from here to here, that halfway point only takes me to here. And then again, and that halfway point only takes me to here. And that halfway point only takes me to here. And then to here, and to here, and to here. And now, I'm already getting to the point that my pen is, again, just a little too fat to actually show the distance that we're actually traveling. The distance itself is so small that we can't actually see it with our eye. But now comes my question. If we keep moving in that fashion, do we ever reach the end? The answer is no. It's a weird concept, but that's kind of what we're seeing with a limit. As we get into this idea of limits, it's not always what happens at the very end, it's what happens along the way to the very end. And we'll very quickly get into the notation to see the difference, why we care, and the difference between those two. But that's where we're going. So in that sense, now again, if we were in class, I would do this by walking across the front of the room, and by the time I start getting over here, my shoes are too big, and that they're eventually just taking up so much of the space, so it seems like we reached our end. But if we truly just had what the idea, the concept of a point, we'd never get to the end. If here I'm 1/10 of a unit away, well then I can only move half of that 1/10 of a unit. And then I would be half of a tenth away and I could only move a half of that. I mean, again, to significant figures, it would eventually feel like we're eventually touching there, but we never actually reach the end. So that is the idea of a limit. So our notation for a limit, the limit of a function f of x as x approaches a equals L. That is our full notation. And what we want to understand here is that the limit of f of x equals L is telling us that the y values are approaching L the closer the x values approach to A. Now, even though this is an intuitive definition, that still is quite a mouthful. And that still is very difficult for people to fully grasp right off the bat. So what I want to be very clear right off the bat is the difference between the limit of f of x as x approaches A versus f of A. This is function notation. This is something we went over quickly in the review video. But the idea of function notation is exactly when the x value equals this A value, what is the y? Here, as we approach this particular x coordinate, what is the y value that we approach? So do you see that subtle little difference? The answer to both of these, this value L and whatever this happens to equal, both of these are y's. This is the y that we actually hit. This is like the y at the end when we look at this exact x, versus over here, this is the y we approach as we approach that particular x. So that's the big thing. Here, exactly what is the y that goes with that x? Over here, what y do we approach as we approach this particular x? So, the easiest way to jump in is to start with a graph. Before we get too crazy into functions and equations, the book kind of does a nice little combination of both. I want to really start off with a graph to fully establish what we're doing with this notation and to immediately start to see the differences between these two. Sometimes they may be the same, sometimes they may be different, but that's coincidence. The understanding of what we're looking for is different between the two. So let's jump in. Let me make a sketch. Here's some function, f of x. Again, as I always say, just making my quick little grid, doing my best, trying to keep things lined up. And let's look at this. There's a lot going on this graph, a lot of funky aspects to it. And again, it's necessary to make sure we understand the difference between these two. So I still haven't really given you any full directions, but I'm already going to jump in and start asking some questions that go with this. But again, to realize a few aspects of the graph, a few things to realize here. Open circles, these are not included points in the graph. Filled in are included, okay? Here we've got a vertical asymptote going through the middle over here. On the ends of the graph, without having a filled in or open circle, we're supposed to assume these things continue. This continues up and away as we keep going up and to the right. This would keep going down and to the left. So it doesn't stop. This graph doesn't start at -4 and finish at +5. We don't need the arrowheads anymore. We have the understanding that these things just continue. So that's, just a few aspects of the sketch and of the graph. And the last thing that I want to point out, well, two things, is that as I pointed out here, that's a filled in point. That's a filled in point. Sometimes you need the emphasis to show something is filled in, but to realize everywhere over here, these are all filled in points. I need to emphasize this because I've got to jump. I need to emphasize this is open, that there's a tiny little gap in the curve from here to here, okay? I need this dashed line to show that these sides don't touch, that they just continue shooting down forever. So again, just some reminders about graphing, but now let's already jump right in, and let's start over here, out here at x is 4. Number 1, let's take a look at the limit of f of x as x approaches 4 versus number 2. Let's evaluate f of 4. And let's start with this one. This is the one we should know. F of 4. I go directly to an x coordinate of 4. Remember, your xy axis is just there just to keep track of where stuff is. It's not the graph. So I'm not on the graph here. I'm just looking at an x coordinate of 4. And now I'm looking directly above and below, trying to find the filled in piece of graph that goes with that x coordinate. And that's what this filled in point is for. This is the point that goes with the x value of 4, and it has a y value of -1. Therefore, the answer to number 2 is -1. Just that simple. Go to the x coordinate, find the graph, there's the y to go with it. But now, when I come back to problem number 1, and I go back to the idea of the limit is all about approaching 4. So as I approach 4, and when we say approach, we're not talking about 1, 2, 3 are approaching 4. We're typically meaning a close proximity. Sometimes the book will go 1 unit away. I typically like to think about a half a unit away. That's what we mean by approaching. So if I start at about here and I get closer to an x value of 4, what is happening to the y? Same thing on the other side. If I start about here and go closer to an x value of 4, what happens to the y's? Well, let's do one side at a time. If I'm on this left side, point, 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 my y's are going up, going up, going up. My y's are going up. And the closer I get to this x coordinate of 4, the closer my y values are to the y at this open circle. Similar on the other side. On the other side, I remember, don't just go left to right. We're always going towards the x value. So don't go away. Start here. I'm starting away and I'm going closer, 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 closer to this x coordinate. So these are the points leading up from the left. These are the points getting closer to this x from the right. And do we notice that they're approaching the same thing? They don't touch, and they don't have to touch in a limit because we're not actually reaching the end. We're just seeing what happens as I get close to the end. And from both sides, the closer I get from the left, the closer I get from the right, my points are approaching this open circle, and that open circle has a y value of +1. So right off the bat, we have a good example of a situation where the limit and the function value do not equal each other. And again, they're not supposed to. They might. It's just about what happens. We can't say whether it should or should not. It's about what actually happens. And sometimes when you're approaching a value, you get the same thing that happens exactly when you're there. Sometimes you do not. And here, I don't care that 1 is 1 and -1, if this was 2 and 1 or 5 and -6. It's just that they're different values. And that's because what happened is we approached. When I say approach, some people start to realize, does the graph come together? It doesn't have to touch here, but is the graph coming together? Where it comes together is the limit value, the y that goes with it. But again, once we go to the original function notation, we don't look left or right anymore. We go directly to that x coordinate, and what is the y that goes with it? So let's keep going, everybody. That's only one example. It's a good one to get us started, but I want us to test several other, that's why I made this first graph pretty complicated. I want us to test several spots. So number 3, we're going to take a look at the limit of f of x as x approaches -3. And number 4, we'll just look at f of -3. And now the order doesn't really matter. Again, we're just going to do both. We won't always do both. I'm just, again, trying to point out, while we're learning about limits, trying to make sure we're not getting the wrong information, that we're understanding the difference between these two. So I'll still start with the function value. F of -3, there's x is -3, there's the point that goes with it, and the y value is -1. Done. This is another good example, everybody. When we start getting into more of the formal limit rules, we're going to need those for equations. With graphs, it's always this easy. We don't even need the formal definition. Just having this intuitive definition, it's just about knowing what you're looking for. And here, I look at the x, find the y, and I'm done. Here, now I look at what happens as I approach this x. And in this generic notation, the idea of approach, x approaches a, that always implies from both sides. So now back to, there's -3, but I'm going to approach from the left and from the right. And from the left, these points. From the right, these points. And just like we saw over here at x is 4, as I got closer and closer to 4, my points were coming together, not touching, but coming together here, and that y value was the answer. Now, not only do they come together, they also touch, but that's irrelevant. The point is that they're coming together, and where they come together, the y value is the answer, is our limit. Okay, so now we see an example where the limit and the function value are the same thing. And some people will start to realize when nice stuff happens on the graph, that's common that these are the same thing. But this is a difficult section because to really understand the limits, you can't just understand the nice stuff, you have to understand the not nice stuff. So now maybe having that in mind, now you can probably guess, we're going to now take a focus at x is -2, something weird happens here. At x is 1, there's another place something weird happens. And at x is 2, we've got another weird spot. So let's set those up. Number 5, I'll come over here, give myself some room. So number 5, we're going to take a look at the limit as x approaches -2. And number 6, f of -2. Now I'll do the limit first, just going in order. So the limit from the left, from the right, we're once again coming together at that open circle. These points here, these points here. Now, a little coincidence. From the left, the points are going up. From the right, the points are going down. That is completely irrelevant, everybody. If this was our piece right here, the same thing would happen. These points would now be going down. These points would also be going down, but they're still coming together. Not touching, but coming together, approaching the same y as we approach that x. And in this case, that limit value would equal 1. We're coming together at the open circle, which forms at a y value of 1. But now this is a little bit of a weird one. What about f of -2? For this part on the graph, okay, no more left or right. If I just look at -2 and just look up and down, what is the point that goes with it? It's a slight trick question. There is no point. This open circle was open to make it clear this is not a part on the graph to go with this x. You go back to this one over here. This was not the point on the graph. We needed something filled in. And over here, nothing is filled in. This is a does not exist. Some people might write undefined. Undefined does not exist. Either way, that is just fine. That is saying the same thing. So that's a situation where the function value does not exist. Let's keep going. Number 7, let's focus on x approaches 1. The limit as x approaches 1. And we'll do number 8, f of 1. The limit as x approaches 1. Well, from the left, these points are taking us up here. From the right, these points are taking me down here. And these two are not coming together. Again, over here, whether it was this and this or this and this, these two sections of graph from the left and the right were coming together. Whether they actually touch or they don't touch, they were still coming together, and that's what gave us a limit value. But here, these are not going to the same place. From the left, we're going up here, up to this point, which would have a y value of 3. From the right, we're approaching this point, which would have a y value of 1. But since we're not getting the same thing, number 7, we're seeing an example of where a limit does not exist. A function does not exist when there's no point of graph to go exactly there, and a limit does not exist if from the left and the right you're not touching. It's not that you're not touching, that you're not coming together. But now number 8, f of 1, don't care about the left or the right, just looking right when x is 1. Where's the piece of graph that goes with it? It's right here. There's the filled in point, and that equals 1. The last two, I'm going to introduce some new notation on my next page, but it's really just reinforcing the same. We just need to formalize the idea of the left and the right, and I definitely want us to take a second round of going through this. This was me leading you, but I want you to have some problems that you can try and run through and then have the answers and the explanation from me right afterwards. So we'll do that in just a moment. and then we will start talking about the equations, but then we'll realize we're still a bit limited and we're gonna need more, and that's where 1.6, we're gonna need limit rules to help handle the rest of the equation problems. But right now, everything we're doing now, you're pretty much set with graphs. So let's just finish this one, and then, like I said, move on, get a little more notation, few more examples, and we'll wrap up this section. So number 9, we're gonna focus on x approaches 2 now. So we're gonna do the limit as x approaches 2, and we'll do f of 2. The limit of f of x as x approaches 2, well, at 2, we see this vertical asymptote. So from the left, my points shooting down forever. From the right, these points are also shooting down forever. Now, not touching, but still going to the same place. The idea of going down forever, well, we don't have a number for that, but we've got a concept. The idea of down forever is the concept of negative infinity. So that does have a limit value. But now when I jump to number 10, f of 2, what is the point that goes exactly with the x coordinate of 2? And it may not look the same, but it's like what we had over here. There is no point. Here we just had an open circle, no filled in point. So there was no function value at negative 2. And the same thing happens over here at positive 2. We've got the asymptote. Remember, the whole idea of an asymptote is, again, the idea of approaching without touching. So if you're approaching this line at x equals 2 and can't touch it, there can't be a point that goes with x equals 2. This is another does not exist or undefined. Now, just before we jump to the next little bit of notes, as I was suggesting, just to realize here, not all vertical asymptotes just give you a limit of positive or negative infinity. You still have to go to the same place. So in this one, if this shot up while this came down, from the left we'd be going up to positive infinity, from the right we'd be going down to negative infinity. That would be a does not exist, just like this one was. Positive and negative infinity are just as different as 3 and 1 are. So over here, we were going to a different spot. The limit did not exist. If this was my graph right here, right at x equals 2 would also be a does not exist. Okay, so now as I flip to the next page, let's formalize a bunch of what we were just saying. So we already have established our limit notation. But now let's make this even more clear. This limit equals f only if the limit from f of x as x approaches a with a minus sign up here. And what that specifically means is we're only approaching from the left. Negative is the left side of our xy axis, so that negative we're only approaching from the left. And that has to be the same value as if we approach a with a plus on that exponent. Again, it's not really an exponent, it's just where you put it. You put it where you would put an exponent, and that would indicate that we're only approaching from the right. So notice, when we were doing these limits, I noted that you have to check from both the left and the right. If you only get a symbol like this, then you only check from one side or the other. You'll always get an answer from these. You'll always have an answer if you're approaching from the left and from the right. And the only way the limit does not exist is if these don't equal each other. So notice, come back over here to the example we were just working on. This was the only spot the limit didn't exist. The limit from the left equaled 3. The limit from the right equaled 1. 3 doesn't equal 1. That's the only time the limit didn't exist. But every other spot where the limit did exist or did not, we got an answer from the left and from the right. And when those answers matched, that was the answer for the entire limit. And when the answer didn't match, that's when we get the does not exist. So, little notation, but now, like I said, let's do a whole nother problem. I've been using F for all my notation, so let's just change it up. For this next one, let's use G. So I'm gonna draw a new fresh graph. So we've got a big, ugly function G here, and just like before, I'm gonna write a bunch of questions. So again, I'm gonna write these out. I encourage you to pause, take a moment, look through these, think about them from everything we said, and then watch. And you'll notice, now I don't expect you to be quite this ready at this exact stage, but what I do expect is that you'll get better and that these graphs, we can move fairly quickly through these problems. So I'm gonna have a bunch of problems, probably like another 10, but after I get them written up and give you a moment to look at them, we're gonna run through, and each one of these is gonna take no more than 5 or 10 seconds. So let's do a bunch. Number 1, the limit of g of x as x approaches -2. Number 2, we're gonna look at g of -2. Number 3, we're going to take a look as x approaches -1 from the left. Limit as x approaches -1 from the right. The limit as x approaches -1. And I'm going to finish a few more over here. Number 7. And my last two stick down here, 11 and 12. Like I said, it's a good time. Pause the video, work on this, see how long it takes you, and then when you're ready, hit play, and I'm gonna jump right in and start going through them. So, x approaches -2. There's -2. From the left, from the right. I don't specifically say left or right, but that's what I have to check. From the left, coming to the open circle. From the right, coming to the open circle, coming to the same spot, which has a y value of 1. G of -2, no point that goes with that x coordinate. That's it does not exist. Number 3, I want to point out, if you were jumping to number 5, you'd be doing 3 and 4 anyway. Just like in number 1, in order for me to get this answer, I had to check from the left and from the right. Whether it's specifically written or not, when you ultimately get to this kind of problem, you have to check both sides. But -1 from the left, so I'm just looking over here, that's shooting down forever. That's got a limit of -infinity. 1 from the right, well, now on this side, now I'm shooting up forever. That has a limit of +infinity. But these answers are not the same. So if I just did this one right off the bat, I'd see I'm not going to the same place. The limit does not exist. But you could always break it down, whether the problem asks you to or not. From the left, -infinity. From the right, +infinity. That is exactly the situation when a limit does not exist. And then g of -1, again, no point to go with that asymptote. That's another undefined point, does not exist. Number 7, Once again, just like I said a moment ago, if you just jump to number 9, you'd be doing these things whether you write them out or not. Jump to number 9. As x approaches 2, well, from the left I'm going up here, from the right I'm going up here. They're both going up, but they're coming to that same open circle at a y of 2. So the limit is 2. Well, x approaches 2 and y approaches 2. That's coincidence. There's nothing special there. I'm just looking at what actually happened. And now realize if I did do these one at a time, from the left, just looking at these, going to the open circle at y is 2. Just looking at 2 from the right, so looking at these points here, still going to that same open circle, still has that same y value of 2. But now the last part, for this one, number 10, g of 2. Well, all this was limits. All this is looking left, right, or both. Here I'm going directly to x is 2. Now I don't care anything about here. I'm looking right at this, and that has a y of -1. And now last piece. I'm jumping, because that's the only problem I have here. X approaches 3, but I'm going to make the note, if you approach 3 from the left, you're up here, right? 3 from the left, you're looking at these, and you're approaching the open circle. So 3 from the left would have a limit of 1. 3 from the right, well, now I'm out here. So I'm looking at these points, and these points are getting closer to this open circle, which has a y of -3. So I didn't have to write this out. I just as easily could have looked from the left, from the right, not coming together. That, by definition, would be a limit that does not exist. But if you want to break it down and go slowly, from the left, you got an answer. From the right, you got an answer. Those answers don't match. That gives you a limit that does not exist. And last, g of 3, same thing. Now I don't care, just like over here, I don't care about any more left or right. I go directly to that x, and that has a y of -1. Okay, a lot of time spent on the graphs, and you'll notice in the homework, that is by far most of your work. But now, what we need to realize is that we can mirror this with an equation. Most of us need our calculators to help us out with this, but we can mirror this with an equation, but we're going to be limited by that. So I'm going to show you this, point out that it works, and for some of the tricky cases that we're going to get into, because just like the graphs, limits, you're only going to really be able to show you understand limits if you could handle the tricky cases. So that's going to come up with equations just like it did with graphs. And we're going to need the algebra. We're going to need the limit rules. So again, it's nice to see this, what I'm about to show you with equations. This certainly could work in a pinch, but you really want to make sure you're getting the good full practice when we get into section 1.6, that you're understanding those concepts and ideas. But for now, again, let's just do 2. Let's evaluate. You notice so far today, all the directions have just been evaluate. Again, those math directions do what the notation tells you. So far we've had limits and function notation, so we're just doing what that tells us. Understanding the notation is a big part. But now, 2 problems. Number 1, let's take a look at the limit of x cubed minus 5x plus 3. The limit as x approaches 2 of x cubed minus 5x plus 3. So this would be like my f of x equals x cubed minus 5x plus 3. But when we have the equation, most people would write that in. We could separately write f of x equals x cubed minus 5x plus 3 and write the limit of f of x. But again, most people just fill in the equation when they know it. But how are we supposed to know this? Again, we don't have any full technique at this point, so what are we really going to do here? And we're going to take that exact description of what we've been doing. We're going to look at x values that get closer and closer to 2 from both sides. I'm going to use values 1.8, 1.9, and 1.99 to approach 2 from the left, and then I'll use 2.2, 2.1, and 2.01 to approach from the right. I'm going to plug these in, get the y values, and I'm going to look at the pattern, okay? So to do this, plenty of people, whatever calculator you have, this is fine. Again, you're not going to be doing 1.8 cubed in your head, so you would be using a calculator. So again, no problem at all if you want to use a scientific calculator for this. I'm just going to take a little advantage of a graphing calculator. I'm going to go to my y equals. I'm going to put in x cubed minus 5x plus 3. And now, instead of graphing, I'm going to use this table button. So second graph will take me to my table. And do I have it set? Nope. This looks like my x's are automatic. I have to just go back to my table set for one moment and change my independent variable to ask instead of automatic. Your independent variable is your x. So when you change that to ask, now I can fill in the x and it'll give me the y's. So I'm going to fill in these x's. Just quickly, my x's. There's nothing special about the x's I picked. It's just some progression. You want to have more than one. You don't want to look at one x. You want to see the progression to see, am I really settling in on this value or am I just kind of close to something else? So you really want to get this, and you don't want to go too far away. You don't want to start looking at x's 0 and 1. Again, about 1.5 to the left, 2.5 from the right. That's about as far away from 2 as you should be. How close should you get at the end? Some people do 1.5, 1.8, 1.9, 2.5, 2.2, 2.1, and that's good enough. So again, there's a lot of little differences, but it'll all get us to the same place. So now let me show you that. So 1.8, 1.9, 1.99. Okay, I got negative 0.168, 0.359, 0.9306. And for me, I don't really notice much of a pattern. A negative y to a positive to a positive. My y's are getting bigger, but that's all I really got so far. So let me keep going. 2.2, 2.1, 2.01. And I get 2.648, 1.761, 1.0706. So here my y's are getting bigger. Here my y's are getting smaller. Are my y's closing in on anything? And maybe some of you are already seeing it. Well, 0.93, 1.07, a little less than 1, a little bigger than 1, it looks like we're honing in on a y value of 1. And by the way, that is the correct answer to this first problem. But maybe that's not close enough. So that's what I was saying. Some people, if you stopped at 1.9 and 2.1, I don't think in this particular problem, other problems, those might be close enough. But if those are the final y's I'm seeing, I'm not seeing a pattern. But maybe I'm still not quite seeing it, so let me get closer. 1.999, 0.993, and then 2.001, 1.007. So if you were unsure here, what y value are we honing in on a y value, and what y value are we honing in on, go even closer, and your y should get even closer to the actual final answer. And that's what we're seeing here. But I think you could already see, I mean, we're lucky that this came out to be a whole number. Certainly fractions and decimals are possible. Not as easy to identify when the calculator is honing in on one of those. At least here we're honing in on a whole value of 1. But even there's still a lot of just little bits that this is not great. And maybe you could already notice, especially for this first problem, a nice little shortcut to getting this answer. We'll formalize that again in 1.6. Right now we're establishing we're still using the idea of a limit. So let x get closer to this x and see if our y's are honing in on a similar one. And for a plane 2, I had to do both the left and the right. So let's finish with one tougher one. Again, maybe you're seeing a shortcut to get this answer, and why is he bothering to do this? I see a quicker way. We'll get to there. But we want to establish the idea before we get into the shortcuts. And number 2 would put a wrench in that. Whatever idea you thought you saw here, This one is going to be a little bit messier. So I'm still going to do the same thing. I'm still going to make my XY chart, and I'm still going to pick the same X's because I intentionally picked this example. Oops, sorry, everybody. I intentionally picked this example so that I'm still focusing on the X value of 2, but I did change my function. So if you're using your scientific calculator to try and get your Y values, just have to be very careful, a lot more careful work to plug in. But with my graphing calculator, again, that quick advantage, I just have to change my Y equals. So, but be clear with my division, I have to establish the top. So quantity X minus 2 divided by quantity X squared minus 4. And now if I go back to that table, oh, actually I changed a little bit. So let me go back to the original, 1.8, 1.9, 1.99. So I'm getting 0.263, 0.256, 0.2506. Maybe you're seeing something it's honing in on, maybe not. Similar with the 2's, 2.2. I get 0.2381, 0.2439, 0.24938. I skipped a few decimal places here. But once again, these decimals getting a little smaller, these decimals getting a little bigger, but there's a lot of decimal points. Do you see them closing in on 1? They are. And let me just take that one step further. If I go 1.999, I get 0.25006. And if I do 2.001, I get 0.24994. Any better? Focusing on this value and this value at the end, seeing the progression, can you see where those two are going? They are finishing at a value of 0.25. So at least that decimal is friendly enough. 0.25 is clean. You'll see we will do this exact same problem after we get those rules established in 1.6, and we'll get the nicer fractional answer 1/4. Because 1/4, again, is a nice one. That 1/4 is a clean 0.25. But if we had something like 1/3, the infinite repeating 0.333 forever, some of those things can be little obstacles. So again, we can do this. This is not terrible, but this is very limited in how far we can take things. And this can really be a way to get bogged down and not really be making good progress. So again, a lot of basics about the intuitive idea of a limit, getting started. We should be able to handle all the graphing problems. This is a nice start with the equations, but after we get the limit laws of 1.6, we'll have a lot more formality that will have alternatives. This one, you'll see, we'll do this one in 5 seconds once we learn the shortcuts. Even with the shortcuts, this will be a little longer, but it will still be more effective than having to try and do this every time.